What's poppin', guys? Today we're going to take a look at our new unit, Related Rates. I would highly recommend that you check out Professor Dave's video. He does a great job walking through exactly what related rates are and what the notation looks like, but I want to keep this as short as possible, so I'm going to jump right into this first example problem. The length and width of a rectangle are changing over time. Write an equation for how the perimeter of the rectangle is changing with respect to how the length and width are changing, and also write an equation for how the area of the rectangle is changing over time with respect to how the length and width are changing. So we have our rectangle, and we've got our sides labeled length and width. First up, I'm going to work with the perimeter of the rectangle, so that we know the perimeter of any rectangle is going to be 2 times the length plus 2 times the width, because it's just the sum of the 4 sides. So now what we want to do is we want to differentiate. And we're going to differentiate with respect to time. So the derivative of p becomes dp dt. The derivative of 2l is 2 dl dt. And the derivative of 2w is 2 dw dt. Essentially, everything is in terms of time, so it's always dt. And that is an equation for how the perimeter of the rectangle is changing with respect to how the length and width are changing. Let's do the same thing with the area equation. So we know that the area of a rectangle is just the length times the width. So the only thing that's a little bit different with this problem is that we need to use product rule when we find the derivative of the right-hand side. The derivative of the area is literally dA dt, represents the change in the area over time. Product rule on the right-hand side, dl dt times w plus dw dt times l. So I just did my a prime b plus b prime a, and now I have an equation for how the area is changing. And again, I would highly recommend you check out Professor Dave's video if that didn't make sense to you. Let's look at our next example. A rectangular box has a length increasing at 2 meters per second, a width decreasing at 1 meter per second, and a height increasing at 3 meters per second. When the length is 4, the width is 5, and the height is 6, how fast is the volume changing? So now this is a problem that deals with actual numbers. So the way that we want to format this is we're going to break it into 3 parts. What do we know, what do we want, and when do we want it? So first, let's start with what do we know. The given information here is that the length is increasing at 2 meters per second, the width is decreasing at 1 meter per second, and the height is increasing at 3 meters per second. Those represent the changes in those dimensions. So the change in length with respect to time is the positive 2. The width is decreasing, so the change in width with respect to time is negative 1. And the height is increasing, so the change in height with respect to time is 3, and it's a positive 3. That's what we know. What we want to know in this problem is how fast is the volume changing. The want is always the question that's being asked. Well, how fast is the volume changing? That would be the change in the volume with respect to time. That would be dV dt. That's the variable that we're really solving for here, the change in volume with respect to time. And when do we want these things? Like, when do we want our answers to be occurring? Well, it's at the moment when the length is 4, the width is 5, and the height is 6. So while those dimensions are all changing, there is one instance when the length is exactly 4 meters, the width is exactly 5 meters, and the height is exactly 6 meters. We want to know how fast the volume is changing at that specific moment. So the great thing about related rates problems is that you can really set up any equation you want as long as it relates the variables that you're working with. We're going to set up a volume equation here just so that we can relate everything. Volume is length times width times height. And the only unfortunate thing about this problem is that we do need to use triple product rule. A, B, C getting multiplied together. So the left-hand side is just dV dt, but on the right-hand side, I'm going to use triple product rule. Triple product rule is A prime BC plus A B prime C plus A B C prime. It's basically all the different combinations. So the derivative of L is dL dt, and then we leave the width and the height alone, plus our next term is going to leave the length alone. Let me just switch colors here so that I can color code it with the right-hand side. And we're going to actually find the derivative of the width, which is dw dt, and again, leave the length and the height alone. And then the last term, we're going to find the derivative of the height, which in this case is going to be dh dt, and we're going to leave the length and the width alone. So that's triple product rule in this context. You can see that it's just every combination of finding the derivative and leaving the other terms alone, and everything is with respect to t. So now we just need to do some substitution. We're going to look at all the information on the right-hand side. We don't know dv dt, so I'm just going to leave that as dv dt. We don't know that. That's our unknown that we're solving for. That's what we want. We do know everything else, though. So now I'm just going to plug in all of those numbers. The length is increasing at a rate of 2 meters per second. The width is 5. The height is 6. In that next term, the width is decreasing, so we're going to use a negative 1 meter per second. The length is fixed at 4 for a split second, and the height is fixed at 6. And then in our final term, the change in the height with respect to time is that positive 3. And the fixed length and fixed width are 4 and 6, respectively. So that's really just a massive substitution of all the information on the right-hand side. That's why it's really important that you guys use the know, want, when format when you're approaching these problems, because they will get challenging. So dv dt is equal to, let's see, that works out to be 60 minus 24 plus 60. So that works out to be 96, I believe. So at the moment when the length is 4, the width is 5, and the height is 6, the volume of that rectangular box is changing by 96 meters per second cubed. And that's our final answer. Moving on to our next question. Two planes are flying towards each other at a right angle at the same altitude. One plane is flying at 100 miles per second and is 200 miles from the point of intersection. The other is flying at 100 miles per second and is 600 miles from the point of intersection. How fast is the distance between the planes closing? Not sure how realistic the numbers are in this context. So again, we have our know, want, when, but I want to make sure that we draw a picture for this just so that we can all visualize it. Think about this as an overhead view of the two planes approaching some theoretical point where they could collide. One of them is 600 miles from that point of intersection, and the other one is 200 miles from the point of intersection. We obviously want to create shapes when we can that help us relate variables. So I can imagine the distance between the two planes helping us create a right triangle in this case. It's really the hypotenuse, that's the distance between them as they move. And it is a right triangle, so we can utilize that. In terms of what we know in this context, we know that one of the planes is flying at 100 miles per second. The other one is also flying at 100 miles per second. Because that distance is getting smaller, right, the planes are getting closer and closer to the point of intersection, because each plane is approaching that point and their distance from that point is getting smaller, we're going to use negative numbers to represent the change in their positioning. So the 100 for both of these planes is really going to be negative 100. Because you can imagine this, the 600 miles and the 200 miles is getting smaller and smaller. What we want to know in this context is how fast is the distance between the planes closing. Note that I used A and B to represent the side lengths for the two legs of that triangle. So I'm going to use C to represent the distance between them, which is like the hypotenuse. So you can see that we're going to set up some sort of Pythagorean theorem here. And you can imagine that distance C is getting smaller and smaller as the two planes get closer and closer together. So we're looking for dc dt, the change in C over time. When we want the information is when one of the planes is 200 miles from the point of intersection and the other is 600 miles from the point of intersection. So we can call A equal to 600 if we want to call it the longer side, and we can call B 200. I really want to emphasize with these problems that as they get more challenging, you really can set up any equation you want with them as long as it relates all the variables. In this case, Pythagorean theorem is going to be most useful so that we can relate all three sides of this theoretical triangle. So I am going to set up Pythagorean theorem right now for my three sides. I'm going to have that c squared is equal to a squared plus b squared. Keep in mind that the thing we want is dc dt. So when I find the derivative of c squared is 2c dc dt, and then the others have similar derivatives, so I'm just going to finish writing that out. Let me go ahead and plug in everything that I know in this context. We do have a lot of information. I'm not going to attempt to color code this time. The A is 600 because it's at that specific moment. The dA dt is the change in A. Similarly, the B is the 200, whereas dB dt represents the change in B, which is, again, negative 100. So I've got everything plugged in, but there is one problem here. Let me simplify the right-hand side before I point that out. The right-hand side is going to work out to be negative 160,000. We have an issue, which is that we have two variables. We have two unknowns. We don't know C, and we don't know the change in C. So in order to figure out the change in C, which is what the question is asking for, I have to first figure out what C is equal to. Remember that C represents the initial length in that triangle, the initial length of the hypotenuse, right? Because at some point, A is 600, B is 200, and in that moment, C has to be a specific number. It's 200 root 10. The way that I got that is just by using Pythagorean theorem with those numbers. So just off to the side, I did Pythagorean theorem, I worked it out, and I got that C has to be 200 root 10 in that moment. And now I can substitute that in, and there's only one variable left behind, which is my dc dt. And now it's not that bad. Now I can just divide both sides, and I get dc dt to approximately be negative 126.49 miles per second, which makes sense in context because remember that we know that the two planes are approaching each other, which means that the distance between the planes should be decreasing. So you should always make sure at the end, if you're expecting the value to be decreasing, you should get a negative number. If you're expecting it to be increasing, you should get a positive number. It will actually align that way. I hope this video was helpful. Good luck on the first related rates assignment.